Okay, so today we're going to do the USACO bronze contest for February 2022. Hopefully this will give you an idea of like what it looks like to participate in a contest, how I would approach the problem and solve them. So we'll get started. So there are 3 problems. We'll start by reading each of them. We'll start with problem 1. Okay, so it looks like we're given like a list of n less equal to 10 to the 5 integers, and we can merge adjacent ones to get the sum, and we want to make it such that they're all equal. And so that's this problem. We want the minimum number of modifications too. Okay, so that's one of the problems. Okay, so this problem, we're given a list of cows and we would like to get them to a certain order. And we can only make modifications that move to the left. Okay, so that's the second problem. Okay, and then there's this one. So we're given a set blocks and we want to spell words with these blocks. We want to know if those are possible to spell. Okay, so my first impressions is that problem 3 is probably going to be a pretty short, like algorithmically, it's probably just going to be implementation. So this shouldn't be too hard to solve. Just going to have to actually implement. When we could do this, if we could just enumerate all possible like words that are generated, because there's 6 letters, 4 cubes. You can permute the cubes and then you can pick the 6 letters. So it's like 6 to the 4 times 4 factorial. This one seems like we can just brute force it. This one is probably some sort of simulation because let's say we have a cow that wants to the left, we might as well move it to the left as soon as possible. And then there's this one. So we do know that the value that we merge them into will have to divide the total sum. And there are a limited number of divisors of 10 to the 6. I don't remember the exact bound. It's probably in the like few hundreds. There's not a nice bound of that, but it's useful to know that like the number of divisors of 10 to the 6 and value up to 10 to the 6 is not actually too many. 10 to the 6 itself has like 49, but you can have more if you pick numbers that have more prime divisors, different prime divisors. So this one also seems like we might be able to just brute force it using that fact. So I think we can start with the third one, because I think this one is the most straightforward if you feel confident you can implement it. Of course, it might be harder to implement. So I'm going to go with doing problem 3 first. The idea for this one, though, just to describe in a bit more detail, we can consider all arrangements of the 6 cubes or 4 cubes, of which we have the number of ways to arrange the 4 cubes is going to be 4 factorial. And we also want to add in the ones that are only 3 of the cubes. You do like 4 choose 3 times 3 factorial and so on. But it's around 4 factorial times the number of ways to arrange them, 6 to the 4. And so this is pretty small. I don't know the exact value of this. It's like, but this is definitely going to fit in time. So we should expect that brute force should pass if we enumerate all the words. The one thing is we have to also do a process. Also have to process n queries. One way we can do this is we can generate all the words and then store them into a list. And so just check. Have we already seen this word? So you either use like a vector or maybe an unordered set. I don't look those up. It doesn't really matter because of the time we're given very few queries, and so looping over all of them words, even if you have to loop over them n times, doesn't really matter. And even if you brute forced for every query, it would still pass because the number of queries is so small. An extra factor of 10 is not bad. So we'll get started by implementing this. Start by coding template. Let's do it just in case. Okay. So in this case, we need to take in words. Cubes, I guess, sorry. Of which there are 4, and then the words of which there are 10. Cubes and words. And then words, and then process. We can start by taking in the input. And then we can, sorry, there are always 4 cubes, I believe. We'll store our possible words into a vector, and we'll want to generate them. Keep our current word. We'll keep the cubes used. And we'll keep track of, that's all we need. Okay. We can add our current word into the possible words. Then we just pick a next cube. Pick cube, and we'll do this recursively. let's say 4 cubes. I guess we can actually use like a Boolean array. Could use a bit set. So you can use integers to represent like a vector of Booleans as long as you, because each bit can represent a Boolean, but since it's a broad contest and we're really not worried about the time, we'll use a vector of Booleans instead. And so if not cubes of used by, then we'll generate, we have to pick the letter. Which there are 6 always, and we'll generate words. The vector will be copied every time, but when you pass into the function, that's not a big deal here because we're not really worried about the runtime of that. So even if we're going to copy it every time instead of like modifying it in place and sharing it, it's not a big deal. So this should generate all possible words. So we can generate words, just have to call it an empty string, Boolean vector. Now we can process the queries. Check into this if it's in the list of words. I'm not sure if vector has a count method. It does not. Yeah, I don't remember. False. So we'll just the words instead. If we find it's possible, we can. I believe that does what we want it to do. We can compile this. We can take the input and see what we get. Yes, no, yes, yes, no, no. I think this does exactly what we want it to. And so I think we can submit this. And this is not the most efficient runtime wise, but the input sizes are so small. That it shouldn't be a big deal. So let's see how it does. So this problem isn't too bad. As long as you make sure during a contest, you should always pay attention to the bounds, because here, you know, you may look at this problem and you'll be intimidated by the fact that like, how am I supposed to efficiently check that, right? Like, am I supposed to prune or like automatically no, or like it seems a little tricky, but if you notice the bounds are so small, right? There's 4 cubes, 6 sides, and the number of queries is less than 10, all of which are very small, right? In fact, we could have probably even done worse because if you look at the runtimes, we're well within the 2 seconds. So if you're, you know, you should always make sure to double check, is a problem brute forceable, especially in bronze, because oftentimes some of the problems really are just implementation. Like, can you implement like a recursive brute force in this case to generate all the cubes or all the possible words? So this problem is done. We can move on to the next one. So I guess we can do number 1 first. If we knew what value, the thing to notice here is for this one, sleeping in class. notice if we knew what the final value was, we can check if it's possible in O of n time. And the reason we can do this is, let's say we knew that we were eventually going to get them to be equal to 3 on the first case. So it would take 3 modifications to get them to 3. The output is not what the final value is, but in this case, we have 1, 2, 3, 1, 1, 1. If you knew they were going to get to 3, then you can greedily do this, right? You just go from the left and you keep going until you hit 3 and you stop. And then you restart and you go until you hit 3 and you restart and you go until you hit 3. And so you can greedily check from left to right. And so this operation makes it easy, and you could consider, one potential idea. Try all final values. Well, the thing is, there are up to 10 to the 6 possible values because the sum of AIs are less than or equal to 10 to the 6. So we could do something that's like O of 10 to the 6 times n, but this would be too slow. Another thing you could try is you could try every possible, if you knew how many elements you were going to split them up into, like if you knew you were going to have 3 sets of 3, or if you knew you had 3 sets, if you knew number of modifications, then we can only try O of n times n possible values. But this won't necessarily pass in time either. This is still, again, we're still going to be too slow. So the trick we can do here is try only number of modifications. Sorry, you can't see what I'm writing. Yeah, sorry. So just make sure I don't remember when I moved away from it. This will be too slow because if we try all 10 to the 6 possible values for the final value, it'll be too slow. If we knew the number of modifications, we can try n of those. But again, that's still n squared, and n is less than or equal to 10 to the 5. So that's still too slow. But instead, if we try only the number of modifications which divide the sum, then this will take O of, if you tried only number of modifications n does the sum, this is at least less than or equal to the number of divisors of the sum, right? And the number of divisors of the sum is like the number of divisors. So we'll write d of n of sum of AI times n. And this may still look kind of slow, but d of the sum of AI is the number of divisors of AI. But since AI is less than or equal to 10 to the 6, this implies the number of divisors of AI is somewhere around, I think, like 1,000-ish. I don't remember the exact value, but it's 1,000 or maybe even a little bit less. And in fact, even in that case, not all of them we can use because they have to also be less than, we also have to like one that gives us actually a number of modifications that can achieve that. And so this isn't even tight. But in this case, something like this gives us a total runtime of about O of 10 to the 8 operations, which of course that's a constant. And so when I say O of like the value, like, it's not exactly what I mean, but also we know that the rest of the operations are very, like, we're not doing much else, not much other work. And here 10 to the 8 should fit in runtime. And in fact, that's a pretty weak bound anyway. But it's around 10 to the 8, probably a little bit less. And so that would pass easily in time, especially with how simple the algorithm is going to be. So this one is just brute force, but you have to make an observation to rule out. Of course, we have multiple test cases. We have to make an operation to rule out some of the guesses you can make. You just have to notice the bounds. So again, making sure to be very aware of the bounds can be very helpful. If you notice 10 to the 6 here, and you knew the bound on divisors, then you might come up with a solution. You can always look up the number of divisors up to like 10 to the power. I think there's a sequence on OAS that tells you that if you really want to know. But in general, you should remember that number of divisors is actually not massive. I don't know how it grows asymptotically, but it's pretty small for 10 to the 6, which if you didn't know that, it makes it a little hard to come up with a solution. But I think this should pass. And this is what I'm going to try to implement. So we'll get a file, put in our template. Here we need to take an input, so we'll process in our test cases. Okay, take an input int n, and we need our array. So A is up 10 to the 5. Okay, so now here we need to do int find modifications. But output answer for this test case. Okay, so we're going to try all modifications. So we can try we can modify it. I guess try all resulting number of values. So 333 becomes 333, which is 3 resulting values. So we could end up with n, which takes the least modifications. So we're going to process them in order of least modifications. We can stop once we find an answer. We're going to need to also find total sum. So we can compute the sum of all the values. We know this will fit in a long, which is important. So we have to check must be a divisor of sum. So if sum modulus I equals 0, then the values will get. Okay, let me make sure. Okay, the values we'll get is going to be sum divided by I, and so we can just greedily check. And now we just need to loop over. We keep track of our current sum. If the current sum exceeds value, it means we are stuck. And this is actually impossible. Break. Otherwise, if it equals the value, we just reset it. In case it's possible, we can return n minus I. Break if it won't. And so we know there will always be a possible answer because, of course, should find an answer. Because of course you could obviously do 0 modification or all the you can put them all into one value and then that would clearly work. But it does complain that we don't return something, even though it can never return. in this case, we can try running this. That is the wrong file. You can ignore the warnings. Those are just because of the compile script I'm using. We do pass the sample. I don't think we need longs anywhere because we're guaranteed the sums are big enough. So that's something to make sure to check. We don't forget to reset data structures between test cases or something. So I think this does what we want and we can submit it. Upload a.cpp and we'll see what happens. Okay, so it looks like it's going to pass in plenty of time. And we do in fact see that this ran very, very quickly because it's very rare for the number of divisors to be very large. And so it's a very good heuristic to brute force off of. So again, this problem is sort of like pretty brute forcey. You just have to make some observations, especially in bronze, like in USACO in general, like a lot of problems, like once you make the observation, the problems can be very easy to implement, right? You just need to make the right observation. And so, make sure you pay attention to all the information given to you. Here, you got to make sure you pay attention to the bounds. You got to make sure, like, if you didn't realize you only test the ones that actually divide the sum, that observation basically solves it for you, right? Like once you know that, it's very straightforward to do. And you don't need to rush into coding, like just take time to think about the problem and see if you can come up with anything and convince yourself that your solution will actually work before you start to code. And in bronze, like, the amount of observations you need to make to actually solve it are generally very small. You just need to make sure you pay attention to all the details. These two were both pretty brute forcey, as long as you were able to analyze runtimes and realize that you could actually brute force them in a way. So the last problem we have is Photoshoot 2. So this is about sorting. This is a sorting problem. But it's a weird sort. This is not a normal sort. We can only move a cow left in an operation, but we can move left any number of times. So in the case of like 1, 2, 3, 4, 5, we can modify this to be like 4, 1, 2, 3, 5, I believe. So that's one modification. I guess we're given 2 samples that we can test with, but in that case, it's one modification. So I think we have to, there's probably a greedy way to just apply this sort and just do this in like something like linear order. Like probably expect something around O of n. And n is around 10 to the 5, so we'd expect n or like n log n. So in this case, one observation. One question you might ask is, and it's always good to try to ask yourself a question if you're not sure where to start. Should I move cow at B1 first? Like, is there any harm in the case of the sample 51324? We need 4 to end up here. Should we move it first and go 4, 5, 1, 3, 2, or should we not? And so the way we can prove this is assume. Let's try to prove this. So assume we had an optimal solution which did not move B1 first. So B1 is moved at some other step. Well, or at least B1 is not moved to that spot. Yeah, I guess you have to be careful. If B1 is moved somewhere else, then you'd have to argue that. Let's say just B1 is not moved, and then we move B1 all the way to the left, right? We could instead move B1 all the way left and then do all the other operations the same way, and this new cal won't get in the way. So we can exchange moves to move B1 first, and solution remains optimal. And of course, if B1 is moved in between and moving more than once, you never want to move a cal more than once because you could have just moved it once to begin with, and then exchanged the other moves to solve them work. So sometimes you'll see, we want to prove that this is sort of a greedy algorithm. We're proving that you want to move the ones that appear earlier in the list B first and just move them all the way to where they should be. We do this with the proof that's sort of a exchange argument. Like assume you have an optimal solution and modify it such that it makes the move you want. And the thing is with greedy solutions, like sometimes it's intuitive, and this problem is pretty intuitive. Like it seems reasonable that you'd probably want to move cal 4 first to the start. It doesn't seem like that would ever hurt you. But if it's not obvious to you, and there's plenty of greedy solutions where it's really not obvious why a greedy solution is correct. Or maybe it's too obvious and it's actually wrong, right? You're like, oh, it seems so intuitive, but it's actually false. So it's useful to try to convince yourself first. Don't rush into coding this and try to convince yourself why. If you want to guess, if you ask yourself the question, should I move this cal first? Try to convince yourself, should I actually move the cal first? Like actually answer your questions. Asking yourself questions and trying to prove them is a great way to try to make progress on a problem. And so that's a great way to start here. And I think that property holds, and I think we convince ourselves of it. And so this shouldn't be too hard to implement. And so we can try to implement this. Okay, so we're going to take an input. So create n is up to 10 to the 5. So we want to greedily move cows in order of list B. So let's imagine we're going to loop over list B. So we have the want to move I into place if it's not already there. So you can check if it's already there is, I guess we're going to need to keep track of 2 pointers. Check at the A index. Okay, so if B of I equals A of A IDEX, then the cow is already in place. And so we can just do A IDEX plus plus, and I plus plus will also happen. So here, if this is not true, we need to move the cow. And the thing is, we don't know where the cow is in A of I. We don't want to actually modify A of I. This would be too slow. So we can't find where the cow is. I mean, we can know where it is, but we can't actually move it there. So instead, what we can do is we can check which ones have been moved. I guess we also need the indices. Index in A of each of the values. We can pre-compute where each is, because that will be useful for us. So here we want to mark it as moved instead of moving it. And so this, now we have to ignore these when we get back. So we'll keep a IDEX the same, but here, while a IDEX of I, or moved a IDEX plus plus. Skip cows, which are already. So in this way, we're trying to do this greedy algorithm, but without actually modifying the list in place. And here we need to keep track of total number of moves. We did one modification. We just have to output the total number of moves. So in this case, we can test it on the sample. Take one. This one should be 0 because the lists are identical. We do in fact get 0. We could test on more cases on our own too, but because USACO doesn't really penalize submissions in order way to check, it's really not usually a concern to worry that much about it. You can use submissions and not really be penalized for them. So I think we have everything we need. We can go ahead and submit it and see how it does. Okay, and so it looks like it passes most of them. Yeah, okay, it passed all of them. So, this bronze contest wasn't too hard. 2 of the problems were very brute forcey, while one of them you really just had to make a greedy observation, which and then kind of just brute force it. And so, like, none of these are very complex implementation wise. Like, the key things you need to know to solve these is you need to be able to make sure you use the information given to you. I think number 1 is probably the hardest because you have to make this observation, but like always remember to pay attention to the bounds. You have plenty of time to think about these problems. Don't rush into coding them. And like the kind of topics you're going to see in bronze, like do tend to be kind of brute forcey, and like, don't, always try to consider like the brute force and analyze the runtime and see whether that will be a possible solution. All these problems did feel like similar kind of ideas you needed. Hopefully this helps you. Hopefully it gives you an idea of like, 1, how to solve these specific problems, and also like what it would look like. How should you approach the problems? How should you read them all? What the kind of topics are and how I would solve them. And we didn't even necessarily implement optimal solutions for all of them. We did for something like Photoshoot 2 because you can't do better than that. I don't know if our solution to 1 is optimal. Maybe there's a better solution. And for blocks, we weren't even the most efficient, but that's fine. We knew what we needed and we implemented what was efficient enough to pass the problem. So hopefully this helps you. Thank you for watching. I hope this gives you an idea of what USACO Bronze is like and how I would approach a contest. And hopefully you guys are able to do well in your next contest. Hopefully you guys do well in this one. And if you're pursuing the next US Open, best of luck. Thank you for watching. I'll end it here.